This video is about trends in the periodic table. We're going to talk about 3 different trends today: radius, ionization energy, and electronegativity. So first, let's talk radius. The radius of an atom is exactly what you think it is from geometry. It's essentially a measure of the size of the atom. The way they actually measure it, because it's awfully hard to measure the size of an atom if you think about that whole idea of orbitals and how we don't really know where electrons are, it's kind of hard to measure the size of an atom. So what they do in practice is they take 2 atoms and of the same kind and they measure from nucleus to nucleus and they divide that by 2. And that's the radius of the atom. That's what they do in practice. But, it's really just a measure of size. Now, of course, all atoms are very, very small, but there is a pattern to the size of atoms. Now, let's do some graphing. On this site, which is www.chemeddl.org, chemeddl.org, you can graph all of these trends and many others besides. So let's graph radius. Let's graph radius for period 2, of the periodic table. Now remember, periods are things that go across, and groups are columns in the periodic table. Alright, so let's graph radius for period 2. So on the x-axis we've got atomic number. On the y-axis we have atomic radius. Now let's take a look at this graph. You'll notice what happens is the radius is going down very steadily. It starts up here at 158 picometers. Okay, really tiny, remember. But there is this change. It starts here. This is lithium, atomic number 3, at 157 picometers. And then it goes down. Number 4 is 112. Number 5 is 86. Here are the numbers right here. Goes nice, steadily downward. Why do you suppose that is? And the answer has to do with the different nuclei of all of these elements. So if you think about radius, let's draw lithium. Here's my lithium. It's got 3 positives in the nucleus, 2 electrons in the first ring, 1 electron in the second ring. Electrons are negative, remember, and a nucleus is positive. So the negative electrons are attracted to the positive nucleus. So they get as close as they can while still staying in their orbits. Now, at the other end of the column, we have neon. Neon, if you'll recall, has 10 positives in its nucleus. It has the same 2 electrons here in the first ring, but then it has 8 out here. So neon is smaller than lithium because it has this stronger positive pull from the nucleus, pulling these electrons in tighter. Now you say, but it also has more electrons, canceling out that positive charge, and that's true. It does have more electrons, but these electrons out here don't block any of these electrons from quote-unquote feeling that positive charge from the nucleus. The only thing in the way of this electron here feeling this 10 positive charge are these 2 electrons on the inner ring. The same 2 electrons lithium has. Here's my radio analogy. You're the electron here in this house, or this electron here in this round house. These positive charge coming from the nucleus is a radio in the middle of the house. The more positive charge, the louder the radio. You're sitting here in this room. There's a one wall between you and the radio, and you can hear it. Here, you're sitting in this room. There's still one wall between you and the radio. Doesn't matter how many people are in the room with you. There's still only one wall between you and the radio, but this radio is louder. So you're more attracted to it, and you head toward the wall to hear it better. So, neon, smaller than lithium. Those electrons are more attracted to that stronger positive, gets smaller across a period. What about down a group? Instead of this, let's do this. We'll do graphing radius versus atomic number for the alkali metals, column 1, group 1. Look what happens. Radius is going up. Now that also makes sense. It makes sense for a couple different reasons. If I'm doing lithium again, here's my 3 plus lithium versus francium down here. Francium has many more rings. It's atomic number 87. So there's 87 positive charges. So the radio's very, very loud. But there's also 1, 2, 3, 4, 5, 6, 7 rings. So you're this electron out here. You're separated by 6 walls from the radio. So even though the radio is very, very loud, you really don't hear it very well. This is called shielding. Okay? Shielding. The electrons, the inner shell electrons, the ones that are tucked away and hidden in the noble gas configuration, all those guys are between the outermost electron and the positive pole of the nucleus. So, first of all, it's bigger because there are more rings. But it's also bigger because these ones out here aren't being held as tight because they just don't feel that positive from the nucleus because there's all that shielding. So as I go down a group, the radius gets bigger. We graph the first 3 periods of the periodic table, you'll see both those trends in action. Along a period, it gets smaller, but from period to period, the radius gets bigger. Down, up, and down again. The D's make it just a little, get it a little off, so we kind of ignoring those. But for main group, it works beautifully. Okay, that's radius. Now we've got ionization energy. The idea of ionization energy is how much energy it takes to remove an electron from an atom. Okay? So specifically, if we're talking about removing the first electron from a neutral atom, that would be called first ionization energy. We have an atom, and then we have a +1 ion and the electron. We removed an electron from a neutral atom and made a +1 ion. That's first ionization energy. Of course, I could keep going. If I did A plus and got to A2 plus another electron, that's the second ionization energy. And so on and so forth. I can keep going until I run out of electrons. But let's just talk for the moment about just first ionization energy. That removing that first electron. In order to understand this, it all goes back to radius. Everything always goes back to radius. Think about that radius trend. As I'm going across, the radius is getting smaller, and the electrons are more and more attracted to the positive. Well, if the electrons are more and more attracted to a positive, it's going to be harder to pull one away. So we would expect, as they go across, the energy it takes to pull away an electron would in fact get stronger and stronger. It would get harder and harder to do that. And that's exactly what we find. Change the y-axis here to first ionization energy. There are the first 3 periods. Sure enough, it goes up across a period. Yeah, there's some exceptions here. But the general trend is the ionization energy goes up as I go across a period. Look at down a group from here to here, from here to here. Ionization energy decreases down a group. Why would that be? Well, again, goes back to radius. If you think about these two with huge difference in their radii, this electron is being held much more loosely than this electron because, again, of that shielding I was talking about. So even though this positive is so strong, this guy out here really doesn't feel it because there's all these electrons in between here and here. So it's fairly easy to get this guy to go away. The bigger the atom and the more shielding there is, the easier it is to pull one away. So as I go down a group, first ionization energy decreases. As I go across a period, first ionization energy increases. These trends are exactly opposite of the radius trends. The third trend we're going to talk about is electronegativity. Electronegativity is the opposite of ionization energy, but it's a little weird to think about because it's the opposite in 2 different ways. One way it's the opposite is it's not a measure of how hard, it's a measure of how easy. The other way it's the opposite is it's not taking an electron away, but it's attracting an electron in. So electronegativity is how easy it is for the atom, neutral atom, to gain an electron. All right, now let's think about that. Once again, this all goes back to radius. So if we think about across, as we go from lithium to neon, got this electron on the outside, which is going to be attracted to one or the other. It's going to be much easier for this electron to head this way because a stronger positive nucleus and also a smaller radius, so that this electron on the outside can feel that's positive much more because it's that smaller radius. So we would expect as we go across, electronegativity is going to increase. It gets easier and easier for that atom to gain an electron. Same trend as ionization energy, increasing as I go across. As I go down, now I've got this electron on the outside. It's actually more likely to be attracted here than it is to be attracted here. And again, it's about that attraction to the nucleus. This nucleus isn't nearly as strong, a positive charge, but it's a lot smaller. By the time that 87 plus gets out here, there's very little of it to attract that electron in. It's much easier for it to go into the 3 plus. So as I go down, electronegativity is decreasing. Again, same trend as ionization energy. And if you look at the graphs, there it is, and you'll see that. As I go across, electronegativity is increasing. As I go down, electronegativity is decreasing. So remember the trends. As I go across this way, radius decreases, Ionization energy increases. Electronegativity increases. As I go down a group this direction, radius increases. Ionization energy decreases. Electronegativity decreases.